Okay, so this is Cop 2, and we begin with sort of the end tail of the integration chapter. Here we are at 5.7, and we're dealing with the natural log function, and basically just how do I integrate it? Okay. Okay, so what is the rule? Basically, if you have a form like this, so 1 over x dx, that's going to be equal to the ln of the absolute value of x plus c. Okay? And probably the real trouble is it always comes in and kind of looks different in the real world, and this is the same thing. How else do they sometimes write it? X to the negative 1 dx, that's the same thing. Okay. So don't be fooled. In general, if you have some sort of u expression in your denominator, this will turn into the ln of the absolute value of u plus c after your u sub. Okay, so let's take a look at an example. Here's example 1. So it's from the book, 1 over 2x dx. So there's more than one way to skin this. You could do a u sub. That's what the book is going to do for you. So hopefully you do your u subs like I do. If not, that's okay. You can do your u sub however you want. Okay, so I'm replacing 2x with u. That sort of transforms it into elementary integral. And then here I have du all over 2 instead of dx. I can factor out my constant of 1/2. And then I have the integral of du over u. And then that's equal to 1/2 times ln of the absolute value of u plus c. And then that's equal to 1/2 ln absolute value of 2x plus c. Okay. Okay, so that's one way to do it. Maybe, in my opinion, a better way to do it is to just factor out the 1/2. Okay, and then it'll be elementary. So I have the integral of 1 all over 2x dx again. So I transform that into 1/2 integral of 1 over x dx. I just factored out the 1/2. You could do that with integrals. Okay. And then it's equal to 1/2 times the ln of the absolute value of x plus c. No, oh no, wait a second, that's not the same thing, right? It's not the same answer, but this is okay. That constant, it works like a seed value. It tells you that you're dealing with a family of curves, and all you have to do is add something in there to move your curve around to get to the other curves. It doesn't really matter where you start it. So for instance, if we rewrote this as 1/2 times the ln of the absolute value of 2 is 2, plus the ln of the absolute value of x plus c, I can now distribute the 1/2, and I get 1/2 ln of 2 plus 1/2 ln of absolute value of x plus c. And then this thing is just a constant. It just shifts it to another place. You can dump that into the c value, and everything is fine and dandy. Okay. So what does that mean? Well, this solution is a family of curves. It's a space of solutions, and you'll have all these curves in here depending on your initial conditions. Okay. This thing is kind of telling you where to, I don't know, start. If you want c to be 0, you may be on this curve. If c is this thing, it's over here. But you could still get to every other curve, is maybe my point. So they're the same answers. Let's look at number 6. So I had 9 all over 5 minus 4x dx. Again, I'm going to do a transformation by bringing the 9 out. Just bring that 9 out. I'm going to leave it. I'm going to rewrite the dx in the numerator all over 5 minus 4x. Okay? Okay. In this section, you're dealing with logs, so there's probably going to be a u substitution you can do to get rid of this denominator. So you're going to just let u be the 5 minus 4x. And then get the differential du. Derivative 5, 0. Derivative negative 4 is negative 4. And then dx. Solve for dx. dx is negative du all over 4. And we're going to substitute that in. So 9 times the integral of dx all over, or sorry, du. Well, I'm going to have to rewrite dx. Okay, so it's 1 all over u times negative du all over 4. Maybe I shouldn't have rewrote it like that, right? Then you could factor out the constant of negative 1/4, so negative 9/4 times the integral of du over u. And then this integral is elementary. I can just write negative 9/4 ln absolute value of u plus c. And then that's negative 9/4 ln back substitute 5 minus 4x plus c. Okay, so what are we doing with integrals? Well, sometimes we want to figure out the area underneath the curve, so let's do one of those. So I have problem 73. Find the area bounded by the region y equals x squared plus 4 all over x, comma x equals 1, comma x equals 4, and then y equals 0. Okay. X equals 1 is a vertical line at 1. X equals 4 is a vertical line at 4. Y equals 0, of course, is a horizontal line on the x-axis. And then to get this curve, I'm just going to plot 2 points, 1 at 1. So when x is 1, I'll have 5 over 1, which is 5. 1, 2, 3, 4, 5. Then when x is 4, I'll have 16 plus 4, which is 20, all over 4, which is 5 again. Okay. And then the thing is going to do something funny in between. It's continuous. Its only discontinuity is at 0. So I don't know what it does. Probably does something like this. I'm just guessing. I don't have time to put it in my calculator. Then I'm going to find this area. Okay, so how do I do that? Well, I do a definite integral from 1 to 4. And then I'm integrating this mess here. Let's rewrite it, right? So let's rewrite it by butterflying it. X squared over x is the same as x plus 4 over x. Okay. The integral of the sum is the sum of its integrals. So the integral of x is x squared over 2. And then plus, if we need to, rewrite this a little bit, 4 integral of 1 over x dx. Ooh, that's the natural log integral again. So remind ourselves we have to still evaluate. Then I have x squared over 2 plus 4 times the ln of the absolute value of x. I'm evaluating from 1 to 4. And we could substitute this information into our antiderivative. So first put the 4 in, so that would be 16 over 2, which is 8, plus 4 ln of 4, minus 1/2, plus 4 ln of 1, which is 0, of course. So it looks like we're ending with 8 minus 1/2. So, 16 halves minus 1/2 is 15 halves, plus 4 ln 4, okay, whatever that is. Okay, so one thing you could do is kind of split these functions up. We could have also done long division. So let's look at one of those. It's Problem 16. Long division turns out to be a very important rule, a very important tool, I should say, not rule, but okay. So here I am. I don't want to try to butterfly this thing. That probably won't work as well as it did before because I have a binomial in the denominator. So instead, what I'll do is some long division and hope for the best. So x minus 2 into the 2x squared plus 7x minus 3. And you have to remind yourself, how the heck did I do that back in algebra, right? So what times x is 2x squared? That'd be 2x. What times 2 is oh, sorry, I'm distributing, so it's been a while. 2x squared minus 2 is 4x, minus 4x, and then you subtract. It works just like it did in arithmetic. If you go back and do some division of fractions, you'll sort of see the rules pop out at you. But here we have 7x minus negative 4x. So 7, 8, 9, 10, 11x, bring down the minus 3. Then we'll have what times x is 11x. So you go plus 11. So you get 11x minus 22. I'm subtracting all that. So 22 minus 3 is 19. And that's our remainder. Okay, assuming that nothing went wrong there. Okay, so how do I write that? I write this plus this all over this. Okay, it's that, I think it's clockwise rotation that we desire. So it's the integral of 2x plus 11, which I'll know how to do. And then after today, I'll know how to integrate this other part, which is just a natural log. Okay. So again, the integral of a sum is the sum of the integrals. So the first 2x is 2x squared over 2, which is x squared, plus 11x. And then plus, if you need to do some more work here, you can go 19 integral of 1 all over x minus 2 dx, and then do a u sub. And of course, the u sub isn't going to result in any sort of oddity. Let's look at it. U being x minus 2 this time, so our du is just straight up dx. So there's no constants to float around, none of that. So x squared plus 11x plus 19 times the integral of 1 all over u du. Du is just dx. And then, of course, that will be x squared plus 11x plus 19 ln absolute value of u plus c. And then that's equal to x squared plus 11x plus 19 ln absolute value of x minus 2 plus c. And that's your answer. Okay, let's look at another one. This is problem 21. So I have the integral of 1 all over x ln of x cubed, like that, dx. Couple ways you can attack this. You can use the power rule to bring this 3 out of the natural log. Okay. So sure, let's do that, right? Then that 3 is essentially just a constant. It's going to be carried out of the integral as 1/3. And then we know we're in the logarithm section, so somehow there's probably a u sub we can carry out. Let's get u equal ln of x. Okay, so the differential du is just 1 over x dx. The derivative of ln of x is 1 over x. And then dx, if you solve for dx, you get x times du. Okay. So I end up with 1/3 times 1 all over x times u times dx, which is now x times du. The x's divide out. I'm left with 1/3 integral 1 over u du, which of course is a natural log integral. So we have 1/3 ln absolute value of u plus c, and then back substituting 1/3 ln absolute value of ln of x plus c. Okay. One good thing about these natural logs, now they open up a door for us. We can go ahead and complete the picture of the integrals of the trig function. So if you remember before, we couldn't really figure out, for instance, the integral of tan. We could figure out stuff like the integral of cosine, right? Cosine x dx. Because we know the derivative of sine is cosine, the integral of cosine must be sine. Because we knew the derivative of cosine is negative sine, we know the integral of sine is negative cosine. But we couldn't figure out things like the integral of tan, okay? Because we don't know the derivative of what function is equal to tan. I don't know off the top of my head. Okay? But now we're going to know that and we can figure it out. So example 8 from the book, and now we're looking at trig functions. In particular, example 8 from the book. We have the integral of tan x dx. And how are we going to do this? Well, we're going to translate tan into sine x over cosine x, and then do a u sub. Okay? So I'm going to let u equal cosine x, the denominator. And so du will be negative sine x dx. In other words, dx is negative du over sine x. So I do my substitutions, right? So the integral of sine over cosine now becomes the integral of sine all over u times dx, which is now negative du over sine x. The sine x's cancel. I have negative integral, after I plot the constant, du over u, which of course is our natural log. So this will turn into negative ln absolute value of u plus c. So that'll be negative ln absolute value of cosine x plus c. And some books don't like this answer with the negative in front, so what they do is the power rule and bring the negative one on the inside and end up with the ln of the absolute value of secant x plus c. So remember, 1 over cosine is just secant. Okay. But either answer is fine. And typically, I like to use this guy. It's just the way I was taught. Okay. So another one, another answer that will be interesting for us is example 9. What is the integral of secant x dx? And this one, generally, I don't expect you to have this one memorized. This one should be memorized. You should know the integral of tan is ln of secant x. This one you're probably not as familiar with, and you probably won't get as familiar with it. But how do I do that? It's kind of tricky. You have to do kind of a multiply top and bottom. Okay, so this will equal the integral of secant x times secant x plus tan x, and it's not something that's intuitive at all. All over secant x plus tan x. Okay. So you end up with the integral of secant squared x plus secant x tan x all over secant x plus tan x. And if you're really familiar with the derivatives, you see, okay, the derivative of secant x is just the secant x tan x. The derivative of tan x is secant squared x. Okay, so you can do a u sub for the denominator, and things will turn real nice. So do my little u sub here for the denominator, secant x plus tan x. And you just end up with the numerator, as your du is secant x tan x plus secant squared x dx. Okay? So this entire portion here just becomes your du, and you're left with an elementary integral du all over u And of course, then that's the ln of the absolute value of u plus c. And then that's the ln of the absolute value of secant x plus tan x plus c. Okay. Well, usually, if one of those comes up on a test, I'll give you this formula. The integral of this is equal to this. But in general, this kind of guy up here, the integral of tan, comes up so often in homework, I expect you to have it memorized after a while. Okay. Well, what shall we do next? Let's just do one random last problem where we actually have to evaluate. It's number 57, and we'll call it quits. The integral from 1 to 2 of 1 minus cosine theta all over theta minus sine theta d theta. Right? So a common theme here has been to let the denominator be your u substitution. So let u be this, and you see this is kind of the derivative of this, and things work out. So we'll let u be theta minus sine theta, and then of course du is 1 minus cosine theta d theta, and then d theta is du all over 1 minus cosine theta. And we can do our substitutions now. So this will equal the integral of 1 minus cosine theta all over u times d theta, which is du all over 1 minus cosine theta. And again, we have this nice cancellation. So it's just du over u. And then that's the ln of the absolute value of u plus c. And then that's the ln of the absolute value of theta minus sine theta. Whoops, and we're not going plus c, right? We have to evaluate going from 1 to 2. So I'm going to plug in 1 and then 2. Unfortunately, I can't do that one in my head. So I'll have the ln of the absolute value of 2 minus sine of 2, and then minus the ln of the absolute value of 1 minus the sine of 1. Right, whatever that is. I did it on my calculator earlier today. It's 1.93 about. Okay, so a very important integral. You'll see it pop up again and again and again and again and again until you hate it. And hopefully after Calc 2 here, you'll be a professional at the natural log, at doing this type of integral. Okay. We still don't know the integral of the natural log, it should be said. But we'll figure that out later on. Okay, thanks, bye.